Thank you. Welcome. Good morning, everybody. I want to, can you hear me okay? Yeah, good. I want to talk, I'm going to make an apology to start with because I'm going to try and sell you a book. But the talk is more than that. I will really want to sell you an idea. The day before I left to come here for this conference, I had a tweet on my surprisingly successful YouTube channel. Sorry, a message, a comment on my surprisingly successful YouTube channel, which said, you should ignore what this man says because he's grumpy, old, and ugly. If that's the basis on which you make your determination of how to do software development, probably not a great idea because then you'll be doing Justin Bieber's version of software engineering. So I want to talk about a different way of thinking about this kind of stuff. I want to talk about a different kind of idea. I want to talk about engineering as a genuine engineering discipline. And one of the books that kind of impressed me that I read a few years ago was a book about theoretical physics a few years ago by a physicist called David Deutsch. And in it, he introduces the idea of science being the finding of good explanations. And he describes good explanations in specific terms. A good explanation should encompass all of the facts, all of our understanding of an idea, and we shouldn't be able to take anything away from that explanation or anything to it. I want to try and give you my shot at giving you some good explanations of what software engineering means. And that's my ambition for this morning. So what does it really mean? And when we start thinking about this, often we start thinking about stuff like this. We start thinking about the production of machines and so on, and worrying about the stuff that we can't afford to go wrong. And this is completely wrong. This is nothing to do with engineering in general, really, but certainly not engineering in our context. This is not our problem. We are the products of the 20th century and the 21st century, and so we're used to the idea of being able to manufacture devices, machines, widgets, whatever they might be, and that's not our problem. Our problem is almost uniquely distinct from that. We write code, and that code turns into a sequence of bytes. And the magic thing, the amazing thing about that sequence of bytes is that it's reproducible for almost free. Essentially, it's a zero-cost operation to clone that sequence of bytes and reproduce a system, whatever its scale or complexity. We can do that if we choose to. And that's a wonderful strength that we have. It means that production for us is essentially a zero-cost step. So production engineering, production is not our problem ever. And I think that's a mistake that we've made over the years. We've tried to apply production line style thinking to solving problems in software, and it's wrong. It doesn't fit. It doesn't work very well because that's not our problem. So what is our problem? So engineering, Alan Kay said yesterday in his keynote talk here at the conference, he said engineering is designing, building, and repairing things in a principled way. So I want to talk about some of the principles. I want to talk about some of those ideas that seem to me to be fundamental to giving us a better opportunity of doing a better job. This is a rather extravagant claim, but I think that the set of ideas that I'm going to talk about this morning, if you were to adopt them and apply them to almost everything that you do, it will guarantee you a better chance of success. It won't guarantee you success, but it will improve the probability that you will achieve success by doing these things. And I hope that you'll agree with me by the time we get to the end. The other thing that Alan said in his keynote was that engineering was about designing for failure, and that's an idea that resonates strongly with me because that's one of the things that I think profoundly differentiates an engineering mindset from not. And that is that in engineering, we start off by assuming that we're wrong. Not that our ideas are right, but that they're probably wrong. And therefore, we work in a way that allows us to be wrong. And that's a good thing. That allows us to learn, to evolve our systems, our understanding, to deepen our wisdom about what it is that we're doing. One of the weird things, and this happened in Alan's talk yesterday, was that we tend to spend a lot of time talking about bridges when we're talking about engineering for some weird reason. I don't really know why that is, but all engineering isn't bridge building. And certainly our form of engineering isn't bridge building. And bridge building isn't what most of us think bridge building is either. So engineering is this multifaceted thing. One of the best examples, I think, at the moment of seeing what real engineering looks like live, and you can kind of watch this happening unfold before our eyes on YouTube, is this. This is Elon Musk's and SpaceX's Starship, the spacecraft that's supposed to be going to Mars one day, that they are building and evolving essentially in public. This is leading edge, bleeding edge engineering. It's doing stuff that nobody's ever been able to do before. And what does that look like? It's not a big Gantt chart where we're just ticking off things as we make progress. It's not a hugely bureaucratic process. It's a process of discovery and exploration. It's a process of experimentation. This is an experiment testing out one of their Raptor engines, a methane breathing, the most powerful rocket engine ever developed so far. And it's about failure. It's about blowing stuff up. It's about trying stuff out and figuring out what works and figuring out what doesn't. It's about doing little tests and evaluating those in controlled circumstances. This thing that looks like a flying water cooler is one of the early flight tests of the first Raptor engine. And then the stuff blows up, goes wrong. But then we learn, and we get better, and then we can fly bigger things. And we end up with something, ultimately, we hope, we're probably going to discover within the next month or two, whether we can actually achieve reuse. We can get a spacecraft that will go into orbit and come back without having to throw bits away. And that's a big deal in terms of space exploration, whatever you think of space exploration. But from an engineering principles point of view, it's fascinating. This is not about coming up with some perfect mathematical model that's going to prove that everything works. They're going to be doing all of the maths, but that's not enough on its own. Engineering is always, the kind of engineering that I'm talking about, certainly our kind of engineering, is always about exploration and discovery. It's about learning. It's about trying to find out what it is that we're building, how it is that we're building it, what the technologies that we're using, are our ideas correct, all of those things. Software development is about exploration and discovery. And that's my starting point. I think that if we are to aspire to become engineers rather than whatever else we want to call ourselves, I think that we must take on the responsibility of becoming world-class at learning, because that is at the core of all that we do. If we are going to take this approach to being able to learn, then we need to be iterative. We are not going to build complex systems. They're not going to spring fully formed from our minds. We're going to evolve them over time. We're going to create them step by step. Iteratively and incrementally. And we need to iterate in order to be able to gather feedback. We need to gather information that's going to inform our decisions, that allows us to make progress and to move forwards. We need to be incremental in that we're going to build these things in stages. We're going to do it bit by bit. As the SpaceX example, they started off flying things that looked like a water cooler, and now they're about to send multi-stage things into orbit, and they do that incrementally, testing out each little attribute of their learning along the route. Excuse me. We need to be experimental. We need to organize our iterative, incremental discovery in a series of experiments. We need to be able to think about what it is that we're trying to achieve, the direction that we want to go in. We want to think about the feedback that we need to collect in order to understand whether we're making progress or not. And make some kind of prediction, and then we test our prediction. And we need to be empirical. I think the thing that differentiates engineering most, perhaps, from science is, we really are more pragmatic. I think one of the mistakes that we as a community, software developers, tend to make when we think in terms of engineering is that we tend to think in terms of kind of mathematical precision and physics or something like that. That's wrong. That's not the right kind of model for engineering in our context. It's more pragmatic than that. We don't need provable systems to be doing engineering. We can do things with less rigor than that. And I think the lure of maths is interesting and useful as a tool, but it's not enough. So these things are really about optimizing to be learning. They're using science as a model to help us direct our understanding. I'm sorry, I'm going to step back because These things are not just a kind of convenient list for me to talk to you here today. These are tools that we can use to be able to guide our exploration and our learning. I think if we apply these things, if we were to stop now and you were to go away and you were to just organize your work like that, without doing anything else, then I think that you would get an improvement. I think that you would learn more quickly and more efficiently and more effectively if you're not already doing all of those things. I think any process that works like this is going to be more effective as a tool to support our learning than any process that omits any of these ideas. That's important because there's not much in software development that we can say that kind of thing about. We can argue in the bar about whether, I don't know, Haskell's better than Clojure or C# better than Java or whatever else. But they don't give us that kind of surety that we're likely to achieve greater success. I think these ideas do. I think it's hard to imagine any approach to software development that's good that doesn't embody these principles. So these are saying something kind of deep, and that means they're a tool that we can use. If we strive to achieve this, I think that doing this, being good at this, we drive out all of agile theory, all of lean theory, all of DevOps, all of continuous delivery as a side effect. Those are emergent behaviors that come out of optimizing for these things. So I think this is saying something important, and that's really what I mean about engineering. These are ideas that whatever your technology, whatever the system that you're building on, these things matter and they work, and they will have an impact on you if you adopt them. The other category of things that are like that, the other category of Alan's principles that allow us to be principled as engineers are these things. We need to also think about the complexity of the systems that we build. We build systems that are too complex to fit into a single human head, fully realized. We build them as teams and huge, complicated things. And so the other aspect that we must take on, the responsibility that we must adopt, is that we must manage the complexity of the systems that we build. And in a similar way to my list of 5 things, there are other things that we can, other attributes, other properties that we can ascribe to being able to do that. We can optimize to manage complexity by improving the modularity of our systems. We'd like to be able to do work in one part of our system without worrying about its impact in another part. We can do that by improving the abstraction in our system. We want to draw lines in the design of our system where I can talk to that other part of the system without worrying about how it works. And so we need to think about abstraction, information hiding, that kind of idea. A tool to achieve that is separation of concerns. It would be much nicer if our systems, each part of our system was focused on accomplishing one task and doing that task well. Excuse me. I've put here loose coupling. I think probably a better description would be, say, to manage the coupling of our systems, but with a tendency towards preferring loose coupling. We'd like our systems to be as loosely coupled as makes sense in the context of what it is that we're doing, because that too gives us this freedom that allows us to make changes in one part of a system and not have an impact on another. This is deeply the idea behind microservices, for example. The whole point microservices, as far as I can see, is that they're independently deployable, therefore you don't get to test them before you release them into production. They are sufficiently loosely coupled that you're able to achieve that. That frees teams to make progress more independently of one another. And the last in my list of managing complexity is cohesion. We want the stuff that's closely related to be close together in the code. The stuff that's unrelated to be farther apart in the code. And we want to optimize for these things. These two are tools that we can use. I would argue, once again, that if you strive to achieve those properties, sorry, I'll step back once again while I'm talking. If you strive to achieve those properties in your code, whatever the nature of the code, whatever the technology, whether you're doing functional programming or object-oriented programming or assembler programming, if your code is modular, abstract, has good separation of concerns, is loosely coupled and has good cohesion, it's better than code that doesn't. These are kind of not really random things. These are not really things that are up for debate. If you've got code that's like that, it's going to be easier to work on. It's going to be easier to change. It's going to be safer to work on, safer to change, more testable, more flexible, more composable. So some of the ideas that seem to me to be fundamental when we start thinking about these engineering principles are, yes, optimize for learning and to managing complexity. But if we want to do that, we need to start taking ideas like controlling the variables seriously. If we want to be experimental, we want to be able to understand the results of our experiments. That means that we need to constrain them. This brings us into ideas like infrastructure as code, good configuration management, good source control, good dependency management, all of those kinds of things. If you can think of a test, if you want to test your system, the properties of a good test is that you want it to be, one of the good properties of a good test is that you want it to be repeatable. That means you want to get your system into the state that you desire it to be in, prod it and poke it to get some result, and you want to get the same result every time given that starting state. That's about controlling the variables. We want to make evidence-based decisions, not just kind of guesswork. Rather than just pointing out that my ideas are bad because I don't look very nice, point out the holes in them, find the evidence, find the data that shows where I'm wrong. And I'll be very grateful to you in that argument where I'm going to dismiss the first one. I've already said this before, and Alan Kay said this yesterday. We begin by assuming that we're wrong, not by assuming that we're right. Ideas are always guesses. And our job as engineers is to then validate or, even better, falsify our guesses. Why do I say falsify? Because that's stronger. Being able to show that it's wrong is a stronger proof than proving something's right. Find ways to falsify ideas simply, and that leads us to more experiments. And I'm not saying, when I say experiment, I don't want to paint some picture of some massively complicated bureaucratic approach to doing things. This can be tiny and practical, and it can take the form of a tiny unit test. That's a form of experiment, and if you think about it in the right way, it can actually make sense as an experiment and as an experimental approach to evolving our systems over time. One of the tools that drives us towards success, I think, a more practical tool that kind of helps us to embody these properties in our code is testability. So, what is it that we value in code? First, it has to work. Second, it's modular so that we can change it easily. You can see where I'm going with this. It's loosely coupled. It's highly cohesive. It's good separation of concerns. It exhibits information hiding or abstraction. These are the properties that I think are kind of table stakes. These are kind of inarguable. You may come up with other properties that you value as markers of quality in code, but I doubt that there's anybody that would argue with these things. And this doesn't matter what the technology is. It doesn't matter what the language is or the framework or the nature of the system that you're building. It doesn't matter whether you're building embedded systems or serverless things in the cloud. If your code is more modular, more cohesive, has a better separation of concerns, it's nicer to work on. It's easier to work on. It's simpler to change. It's more effective to understand it. This is important stuff, I think. So what drives us? What allows us to put that quality into our code? Before test-driven development, I think that there's only one thing. It's down to the skill, the experience, and the commitment of a programmer. If you're talented and skilled, then you might be able to do a good job of achieving modular, nicely cohesive code with good separation of concerns and all of those things. But you also have to care enough on the day whether you can be bothered to do that for this particular piece of code. And you have to have the experience to understand where to compromise and where not to. Test-driven development, I think, is one of those tools that gives us an opportunity that we don't value highly enough, in my opinion. I think that test-driven development is one of the most important advances that we've made in quality systems during my time as a software developer, which is quite a long time, to be fair. Test-driven development is specifically this. It's about writing the test before you've got any code. If you write the code first and then you write unit tests afterwards, that's not test-driven development. The driven part is important. We're going to drive the development of our code by writing tests. That's the red part. So we're going to write a test before we've got any code. We're going to run that test and we're going to see the test fail. I like to call out the nature of the failure when I do this. This is, again, a tiny little micro experiment. I'm making a prediction. I predict that this test will fail with exactly this error message. I run the test. If it doesn't fail with that error message, I've done something wrong. I've misunderstood something. That's a little experiment. It gives me control and allows me to make progress in a more controlled way. Now we're in an unstable state. We've got a failing test. So now we're going to write the minimum amount of code to get us back to a stable point where our tests all pass. That's the green step. We're going to make just enough changes, even dumb changes, hard coding a return value or something like that is enough to get us back to a stable point where we can now go to town. Now we can do the work to make while we're in this stable position of a passing test, we can do the work to make our code more general, more readable, more beautiful, more elegant, simpler. Our test clearer and more expressive and a better statement of our requirements, our needs of the software, and therefore more decoupled from the code. These are all great tools. Think for a moment, whether you practice test-driven development or have ever practiced test-driven development or not, think for a moment what that would mean to your working practices. You're going to write a test first. You haven't got any code yet. You'd have to be a kind of strange, crazy person to write that test to make your life more difficult. You're going to try and take the easy path. That's, I think, one of the hallmarks of good engineers or good software developers is that we're a bit lazy. We want the machines to do the hard work and us to do the nice creative bits. So I'm going to write a test, and if it's hard to write the test, that's telling me something important. It's telling me that my design's not very good. It's telling me that I need to work harder on improving the abstraction, the modularity, the separation of concerns, whatever it might be, to be able to make my code more easily testable. So this gives us this opportunity, this gives us this chance to inject those properties that we value as markers, hallmarks of quality in our code, into our code. So what makes code testable? Well, obviously, we want the test to pass, so the code has to work. It needs to be modular so that we can focus in on one part of the problem and evaluate the behaviors just in that context. And so we're going to prefer to have modular code. It needs to be loosely coupled so that we can deal with this module without worrying about a whole network of other complex dependencies. We want to isolate those in a way in which we don't care about them in the context of a test. It needs to be highly cohesive. We like the bits that are related and change together often to be close together in the code so that we can We can make changes and evaluate those together in a test. That's going to improve the testability of that code and the durability of our tests over time. It needs to have a good separation of concerns. We want to draw lines in our software so that we can focus in on testing one particular behavior of the system at a time. And it needs to exhibit information hiding so that we can write a test that doesn't care anything about the implementation detail. We want to be able to write code where our test expresses only the desirable outcomes of the behavior of our system and not the implementation detail. So we now have the freedom to change that implementation detail. So, before test-driven development, we had this bunch of things that allowed us to put these attributes of quality into our code. And with test-driven development, we have both the skill, experience, and commitment of a programmer. We don't lose those things. We don't throw those things out of the window. Talented people are still going to do a better job than not talented people. But we amplify that talent by using test-driven development to focus us at the right points in the design and development cycle on improving the quality of our output. This is a very good thing. There's not much that's like that. There's not much that amplifies our talent in the same way. I would argue that language choice, framework choice, and so on don't do that kind of thing. They don't amplify the talent of a developer in the same kind of way as this. They certainly have an impact, but they're not the same kind of tools. So this is kind of a multiplicative effect. This is, overall a better thing. It's not going to make a bad programmer great, but it will make a bad programmer better, and it will make a great programmer greater. This is a talent amplifier, and we don't have too many of those. I want to give you a simple, concrete example. I've been talking theoretically for a little while. So here's a bit of code. This is a very simple bit of code. Here I have a car. The car has a petrol engine, and it's got a start method. So we're going to put the car into neutral, we're going to apply the brakes, and then we're going to start the engine. So let's write a test for this. I'm focusing only on the testability of this code and nothing else here. So here's my test. We're going to create a car. We're going to start the car, and I can't assert anything. There's nothing I can do here. I can't actually test this code unless I decide to break encapsulation and dig in and kind of look at the value of some private variable, which is really nasty. Don't do that. So that's a problem. This is not good. Well, this is not good. So let's now look at trying to improve that situation. Again, just purely from the point of view of testability. So here's a better car. And this has a critical change, which is kind of easy to spot. Instead of creating the petrol engine as part of the car, I'm injecting the engine to allow my code to be more testable. So let's have a look at writing the test for this. Here's my test, should start better car engine. So I'm going to start by creating a fake engine. What's a fake engine look like? In reality, we'd probably use a mocking library or something like this, but in this case, I've just written the code to make it obvious what's going on here. So we're going to start the car, and when we start the car, we're just going to record the fact that the car's been started, and then we're going to allow us to be able to query whether the car was started or not after the fact. So now here's my test, here's my better car with the fake engine. I'm going to say start, and now I can ask whether the engine got started or not. That's a simple change. That's nice and easy. But think about this from the point of view of what this meant for the code. Sorry, let me step back a little bit. Think about what this meant from the point of view of the code. Injecting this engine is what I would call adding a measurement point into the design here. The engine allows us to observe behavior that is otherwise unobservable. You can think of it as kind of having a place where you can kind of put a probe to measure a behavior of the system or something like that. So we're injecting a measurement point into our code, and that's an impact on our design. Think about what that means in terms of this design. This code is now more modular, because now we've separated the idea of car from the idea of engine. And each of those things can be more independent of one another. It's more, we haven't really changed the abstraction much in that sense, but we've certainly hidden information a little bit more because we've hidden the way in which we actually create the engine. Before we were more tightly coupled to the engine because we were constructing a specific engine. It's improved, it's more loosely coupled because now we don't care what kind of engine this is. The result of all of those things is that now I can still create a better car with a petrol engine, and this is exactly the same as it was before. But the code is more flexible. Now, without any changes to the code whatsoever, I can create a better car with an electric engine, or if I'm some kind of crazy person, a better car with a jet engine. This is a powerful idea. This has made my code more flexible. It's made it more useful as a tool, more composable, just more useful, more valuable. This is better code because we've made this change to make it testable. By striving for testability, we've improved the quality of our code. That sounds like something that engineers would say about adopting a certain kind of discipline and getting a better outcome as a result to me. Another one of those tools that I've already mentioned is working experimentally. So what does that take for us to work experimentally? Excuse me. We need to think about testing things in parts. SpaceX didn't start off by building the whole spaceship, sending it up to see if it went to Mars or not, and then go, oh damn, that didn't work. The waterfall approach doesn't really apply to the kind of engineering that I'm talking about here. We need to be able to try stuff out. We need to assume and expect, and we will make mistakes. We need to allow ourselves the freedom to make those mistakes and to learn from them. These are the points when we learn the most, the point at which stuff goes wrong. That didn't do what I expected. And that's when you're really learning. That's when you're really making progress, actually. It's one of the kind of superpowers of science and scientific style of reasoning that's the fact. That we learn more when we make mistakes than we do when our predictions are matched by our experiments. We want to make progress in small steps. We don't want to risk too much. We want to break problems down into smaller pieces and incrementally build on our learning and understanding as it deepens, as our understanding of the problem deepens, as we get feedback from our users about what they like in our products or not, and we get feedback from our technology about what works and what doesn't, and we get feedback from our design about which directions are effective, and so on. We want to gather the feedback. We want to think about, at each stage for everything, we want to think about, how will I know whether this worked or not? Did this idea move us forward in the direction that we want to achieve or not? And you want to establish measurements that are in some form, subjective, qualitative, whatever the nature, but measurements of some form that are going to indicate whether you're closer towards your goal or further away from it. And then you adapt based on whether you're moving in the direction of your goals or not. We want to try and predict the results. If we're going to be experiment, don't just try stuff out and then randomly kind of wander around looking for things. Try just by, do that test thing. When you write the test, think, what is the error message going to be? That's just a slightly stronger statement and a slightly more disciplined way of organizing our thinking that gives us better results. And focuses us on a bigger scale on what the feedback that we need to collect is and the understanding that we need to gather. We need to control the variables so that we understand the results of our experiments, and this drives us in the direction of creating code that's more deterministic. One of the impacts that this has had on my own design is that I don't write concurrent code anymore in the guts of my problem domain. Concurrency is always isolated and treated as a separate concern at the edges somewhere, because that makes my code more deterministic. That means it's more testable, more effective. It also has the side effect of meaning that my code's faster as a result of this. That's maybe counterintuitive. If you're interested in that, look up some of my stuff on reactive systems. This is a diagram that I've been using for some years now to describe continuous delivery. And continuous delivery, I think, fits into this model quite well. This is a series of feedback loops. There are many more feedback loops than this, but at the outside, we've got the kind of principal feedback loop that drives the continuous delivery process. We're going to optimize from having an idea to getting that idea out into the hands of users so that we can collect the feedback and understand what lands with our users and what works. At the center, at the core, we've got the fast feedback loop that I've just described with test-driven development. We're going to write a test, see it fail, write some code, see it pass, refactor and tidy up, commit and move on. And then in between, we've got other kinds of evaluation. Is our software releasable? Is it fast enough? Is it secure enough? Is it scalable enough? Is it regulatory compliant? All of those things. This is a quote from Richard Feynman, the Nobel Prize-winning physicist. It doesn't matter how intelligent you are, if you guess, and that guess can't be backed up by experimental evidence, it's still just a guess. So if we want to be engineers, we need to start moving in the direction of relying less on guesswork and more on experiment and evidence, measurement. The other tool in our arsenal is speed. And this might sound a little bit weird, but one of the findings, one of the things that we've learned in recent years is that there is no trade-off between speed and quality. In fact, it's quite the reverse. If you want to build code quickly, you must focus on the quality, because otherwise you spend way too much time fixing all the crap that you wrote earlier on. If you want to build code with very high quality, you want to optimize to get really good feedback and insight and make progress in small steps, so you need to move really quickly. So speed and quality are not trade-offs between them. I make my living these days largely as a consultant, mostly for big companies, mostly adopting continuous delivery or improving their software engineering processes. And I'll give you my secret sauce for free. Basically, my secret sauce is optimize for speed. That's it. Optimize so that your software is always in a releasable state and you can determine that multiple times every day. However you do that, if you can do that and it's true, there's no more work to do after your deployment pipeline says it's releasable, you're doing a good job if you can do that multiple times a day, and your software quality will be higher and your process of developing it will be faster. It's a side effect of that. Now, unfortunately, it's actually quite difficult to do that. It takes quite a lot of things. But nevertheless, this is a tool that we can use. This is a measurement that we can use. We can start measuring the efficiency of our development process. This is a value stream analysis from a software project that I worked upon. And this couldn't release a change into production, however simple, in under 106 days. Basically, no feedback. This is a project that was about 15 to 20 times bigger than that, where we built one of the world's highest performance financial exchanges. We could make any change to our entire enterprise system and evaluate it and get a definitive answer, is this releasable, in 57 minutes. That's a different game to be playing. That's a different game to be in. Continuous delivery is built on these kinds of ideas. I'm not going to go into the detail. If you're interested in this, forgive, I'm going to sell my other book now. Go and have a look at the continuous delivery book or the continuous delivery pipelines book. At the core of continuous delivery is the idea of the deployment pipeline. And I think the deployment pipeline is often misunderstood. The deployment pipeline is not just a build or deployment automation. I think it's partly Jez Humble and my fault that it's misunderstood, because we kind of put that as the subtitle of our book. But the deployment pipeline is actually more than that. The deployment pipeline, I think, is most usefully thought of as a definitive statement on the releasability of your software. We're going to go from commit to releasable outcome. And whatever it is that it takes to determine the releasability of our change is within the scope of the deployment pipeline. If you can't, at the end of your deployment pipeline, if you can't say, if all the tests or all of your evaluations in the deployment pipeline passed, you can't say, good, I can just push that into production with no more work. It's not really a deployment pipeline yet. This kind of divides up into several different parts. The first part is really about continuous integration, and my advice is that you optimize for speed. You optimize to get feedback on, does this code do what I as a software developer think this code does? And you get that answer back in about under 5 minutes, ideally. And then there's the rest of it, which is really about the releasability of our change. Is it fast enough? Is it resilient enough? Is it secure enough? Is it regulatory compliant? Whatever it is that determines the releasability of your system. And my advice is that you aim to get an answer to that in under an hour. Now, this might sound easy or impossible depending on where you're at in your journey and the nature of your system, but I would point out that Tesla do this for cars. You can do this on a vast scale. Google have a single repository with 25,000 engineers committing to it, and they get responses back about the releasability of their changes in minutes. So you can do this at vast scale in complicated scenarios. That doesn't kind of close this off. The other thing that Alan Kay said during his talk yesterday was that engineering was, you could characterize engineering as design, simulate, and build. I quite liked that model. And I think this is deeply embodied in deployment pipelines. You can certainly characterize the bits that I've just pointed out. The first stage really is nearly all about design. This is technically focused and is giving developers feedback on the quality of their designs. I would argue that that's one of the principal values of this stage in a deployment pipeline. This stage is about simulating the behavior of our system in a way to determine its releasability. We're going to try it out in all kinds of different ways. And the last part, if you followed my advice, the last part is almost free, because the build step is, we've just evaluated all that stuff in simulation. We just cloned the bytes. One of the remarkable things about software compared to anything else, if you're building an aeroplane these days, or a car, or a bridge, you're probably going to have a sophisticated computer model of the system that you're building, almost inevitably. But that's not enough, because that sophisticated model, however sophisticated, isn't reality. For us, the thing that we test isn't our model that we're testing and simulating, isn't the model, it's the real stuff. So we have that advantage. That's a fantastic advantage for us. That gives us the opportunity to make the build step and reduce it significantly so that it's almost a non-event. Forgive me advertising a little bit, but if you'd like to know more about these kinds of ideas, I run a YouTube channel which talks about continuous delivery, software engineering, and I publish videos every week. There's a lot more on all of the stuff that I've talked about, and there's going to be more on all of the stuff that I've talked about. So take a look at that. I also promised you that I was going to try and flog you a book. I've written this book, which is called Modern Software Engineering, which is I've just outlined the structure of what this book is about. It goes into much more detail and much more examples of how you can use these things as tools and so on. And it's not yet out. It's released on December the 6th in electronic form, and in paper form, hard copy form in February the 6th. But there's if you pre-order, the publishers have given me this code, and so you can get exclusive to people that kind of listen to me talk and bore you to death, is that you can get a 35% off the cost of the book. So if you're interested in following up more and understanding more about this kind of idea, take a look there. I confess, I'm getting towards the end of my career. I might be old. I'm not going to comment on the ugly. I'm certainly grumpy sometimes, as my family will attest. But one of the things that gives me the freedom to do is to start tilting at windmills a little bit. My ambition, and it is a lofty one which I don't expect to achieve, but my ambition is I'd like to change the way that we as a community think about software engineering. I'd like to try and change, define some of these principles that we can just agree. These things matter, and we can evaluate almost any idea against these things. If you want to adopt a new technology, does it allow you to iterate faster? Does it give you better feedback? Does it allow you to create more modular systems? Does it allow you to test those systems more effectively? You can use this as a model to evaluate that kind of stuff. You can look at it in terms of evaluating designs. Is my software good or bad? Is it modular? Is it cohesive? Is it got good separation of concerns? Because that will answer the question for you. Using testing to drive these behaviors into the system gives us a tool that we can use. We can use this to create higher quality systems. And the results of creating those higher quality systems is quite dramatic. The other thing that I talk about in the book is metrics, and the DORA metrics, the stability and throughput metrics that are behind the State of DevOps report and are described in some detail in the Accelerate book, give us a tool that, again, we can evaluate ideas against. Does this improve the quality of my output, the stability, measured in terms of the change failure rate and the time it takes to recover from a failure? Or does it improve my throughput, the frequency with which I deliver changes into production and the lead time that it takes me to go from commit to something releasable? Organizations that have good scores in stability and throughput make more money than organizations that don't. Teams that have good that are qualified as high performers in terms of measurements of stability and throughput spend 44% more of their time on new features than teams that don't. So this is a commercial imperative for the organizations that we work in. So next time your boss comes to you and says, we're under a bit of a deadline pressure, you need to be able to push these features out faster. You say, right, I understand what you're telling me, boss. You're saying we need to do more testing, more high quality design, more refactoring, because that's what the data says makes us go faster. It's not cutting corners. It's not ignoring those things. It's not ignoring quality. Doing high quality work pays. And we've got data to back that up. Thank you very much indeed for listening. I hope you have a great rest of your time at your conference. And I'm very happy. I think we've got a few minutes for questions.